Okay.
I don't know. I just heard about it.
They installed Face ID for the iPhone X. It doesn't have a button. So the guy demonstrating on the stage, he failed to unlock for Face ID. So yeah, that.
How do you turn off? Doesn't have any buttons.
It has a power button on the side, but the screen button is not. So instead of just hitting the home button to exit and that, you slide up to exit. Right? Just to have some extra screen.
Okay.
Why can't they?
Why can't I just print money for doing bullshit?
Okay. All right. So I'm letting you guys choose. What we want to be what we'll be talking about today. We can continue to talk a little bit about scientific notation. How to parse and stuff like that. I can give you examples using a spreadsheet of how to do the actual conversion from M10 to M2, from E10 to E2. Or we can move forward and talk about memory units, the smallest memory units in the computer, and then start from there. So where did we stop last time? Did we finish the entire discussion of converting to a double?
I know we were close to the end.
We were close. Okay, so let's go back there first. Okay, so we will recap floating point number representation. And because I'm teaching two sections of the same class, sometimes it's, unless I watch my own video recording, it's pretty hard to remember, where I stopped with each particular class. But I'm pretty sure with this class, I talked about the loop, how to get rid of E10 when E10 is less than 0. Okay, and I'm pretty sure we talked about how to get rid of E10 when it has a value that is positive to begin with. So I'm pretty sure we got through this, okay? So what we may or may not have done is the normalization of the mantissa.
I think we were there.
And I made a mistake, in one of these things, like the M2, the 2 is outside. I think, that was a mistake that I fixed here. Okay, so let's start with 5.3, the normalization of the mantissa, okay? By the time we get here, the mantissa is a base 2 mantissa already. In other words, we do not have any exponent of 10 left to specify the magnitude of the number. Okay, we only have, or you can say that E10 is a 0, so it's gone basically. So at this point, what we want to do is to look at the huge mantissa that we have. Now the mantissa is huge because we want to keep it large to reduce the errors. Because when you're dividing by 10 or dividing by 2 and you start with a small number, then the part that you lose because of rounding is going to be big. So you want to keep the mantissa as big as possible so that every time you divide it by 2 or divide it by 10, your error is small. Okay, we want to keep it as small as possible. So that means by the time we get to section 5.3 in your actual algorithm, M2, which is basically M from the end of the previous step, is going to be a pretty big number. Okay, it might need 60, 62, 63 bits to represent. Okay, that's a pretty large value. But that's not what we want M2 to actually be when it is all done, because we only have the mantissa in binary is supposed to be 1 point, okay, and then followed by 52 digits, 52 bits. In other words, your actual precision is only 53 bits, counting the 1 point. Is that okay? So when you have a 60-something bit, number, it's not going to fit. So what we need to do is to figure out, okay, so how do we shrink it so that it is the right format? This part is just theoretical. It's actually not needed here. So I'm going to start with the part where this is actually practical. So as long as M2 is less than 2 to the power of 52, it doesn't have enough digits. Okay. So when M2 doesn't have enough digits, we're going to have to give it more digits. So the easiest way to give it more digits is to multiply the mantissa by 2, like that, and then we'll decrement the exponent by 1. So we'll keep doing this until that number is at least 2 to the power of 52, which requires 53 bits to represent. Okay, the value 2 to the power 52 is represented by 1 followed by 52 zeros in binary. Is that okay? On the other hand, if your mantissa is way too big to begin with, it is greater than or equal to 2 to the power 53, which requires 54 bits to represent, then we try to shrink it. Okay, and the way we shrink it is to use the rounding technique, divided by 2, and then every time we divide it by 2, we adjust E2 by incrementing E2 by 1, so that we are not changing the value that we are representing, we're just changing the way it is represented. Is that okay so far? Okay. So by the time you're done with these two loops, okay, now by the way, these two loops do not need an if then else statement to separate, because there's no way you can get into both loops. Just because of the condition of the loops, there's no way you can get into both loops. So by the time these two loops are done, what do we have? What is M2? How do we analyze this program and say, okay, by the time these two loops are done, what is the range that M2 can fit into? Just looking at the conditions of the loops. Okay, to get out of the first loop, M will be greater than or equal to 2 to the power 52. But to get out of the second loop, M2 has to be less than 2 to the power 53. So that means at this point, we are staring at the answer right here. Okay, we're staring at the answer here. So by the time we're done with these two loops, we are guaranteed that M2 is greater than or equal to 2 to the power 52. It is also going to be less than 2 to the power 53, which is great, because how many digits do we need to represent M2 when it is within this range?
50.
Exactly 53 bits. Okay, exactly 53 bits. Now, why we need 53 bits is because the 1 point, okay, of the mantissa is not represented anywhere within the actual double. So that's why we want the number to be 53 bits, so that we can just chop the most significant bit, keep the rest, and we're all good. Is that okay? All right. So what we need to do is, we need to chop the most significant bit. This is one way to do it. Okay, we can say, actually, this is correct. Okay, so you can say, M2 stores, we want to store the modulus of 2 to the power 52, which will basically return the remainder of the division, using 2 to the power 52 as a divisor. And that will basically chop the most significant bit. Okay. But personally, I would not use this operation. I would use a bitwise AND to chop bits. Okay. All right. So this is a good time to talk about bitwise operation and why bitwise AND is very handy for doing certain things. And I think for this, I'm going to use a spreadsheet, because a spreadsheet is already a table. It makes it easier to understand, to visualize bitwise operations. Okay, so I'm gonna, doesn't matter what we have on that particular sheet, I'm just gonna start a new one. So what we want to do is look at bitwise AND. Okay, so this is bitwise AND. And instead of using 64-bit numbers, which will take me a lot of time to write all the zeros and ones, let's just focus on 4-bit numbers. Is that okay? All right. So let's say we start with A, B, C, D. Okay, so A, B, C, D are individual bits. Okay, and the second number I'm going to use I'm not going to use variables here. I'm going to use actual values here, zeros and ones. Okay, so I'm going to put a 0 here, a 1, a 1, and a 1 here. Okay, let me resize the columns a little bit, because otherwise it's a little bit, oh, that's not what I want to do. Okay, let's do it one more time. Resize all of these at the same time. There we go. Okay, this is cool. All right, what is D and 1? D is some bit that can either be a 0 or 1. So what is D and 1?
D and 1?
Anything and 1. 1 is true, by the way.
True, yeah.
So anything or true and true is whatever you start off with.
Oh, yeah,
Not
perfect.
true.
Yeah.
Whatever you start off with, which is D. Okay, same thing with C, same thing with B. What about A and 0?
False.
A and 0 is false or 0. Okay, so effectively we just chopped the most significant bit. We turned the most significant bit to a 0. This is an example using only 4 bits, right? But you can also imagine, okay, if we have 53 bits, okay, and you have the most significant bit, you have a 0 corresponding to the most significant bit of a 53-bit number, and the rest are all ones, you would achieve exactly the same thing, which is getting rid of bit 52 and keeping all the other 52 bits intact. Is that okay? Sort of.
So you only look at the most significant bit when you do bitwise AND on a.
Well, you can do it anyway. I mean, you can turn this one to a 0 if you want. I don't know why you want to do that.
Yeah, but like, how does it make it work specifically for one thing? Like, because if it's like a giant string, like if it's a variable, how do you specify like the specific one that's going to AND
okay,
on?
very good. So how do you specify a specific bit, and it is the bit shift operation. So that's your best friend in this case. So let's go ahead and take a look at the two alternatives. So I can say m2 equals to m2 mod 2 to the power of 52. Okay, so and there's no easy way to do it in C and C++. So this is I'm trying to use C and C++ syntax here. Okay, and the quickest way to do it is really just to do this. That's 2 to the power of 52, because you're shifting to the left. You're shifting 1 to the left 52 times. So you end up with 1 followed by 52 zeros, which is 2 to the power of 52. Is that okay? How many people are not familiar with the bit shift operator? Okay, so let's go ahead and talk about the bit shift operator. So I'll give you certain assertions, okay? So 1 is the same thing as 1 shifted 0 times. Is that okay? Does everybody buy this? Okay, we have a bit pattern that is representing 1, which is 1 with all the more significant bits being 0, and I'm saying let's not do anything with it. We're shifting 0 positions. Okay, fine. I would say 2 is 1 shifted once. 1. So bit 1, okay, the bit pattern representing 1 is just 1, right? So when you shift it to the left, you're padding the right hand side with zeros. So now it becomes 1 0. 1 0 in binary represents 2, the value 2. Is that okay? So what about 4? It's 1 shifted twice. 8 is 1 shifted 3 times, and so on. Is that okay? Yep.
But how would you do like 3, for example, or 5?
3.
Or only for 1, 2, 4, 8, 16.
You can do other operations. Okay. So let's say I want to only use bitwise operations and only the values of 1 and and shifting to get to specific values. Okay, let's say 5. Okay, so what is 5? 5 can be represented this way. 5 is 1 shifted 0 times, bitwise OR with 1 shifted twice. Because 1 shifted 0 times is 0, 0, 0, 1, right? Okay, as a 4-bit pattern. 1 shifted twice is having 2 zeros to the right of the 1, which makes it 0, 1, 0, 0. When we look at the entire thing as a 4-bit number, right? So the single bar is bitwise OR. It is not logical OR. It is bitwise OR, which operates the same way as a bitwise AND. You take bit 0 and bit 0 of the 2 numbers. You perform a OR, and the result of that becomes the result, bit 0 of the result. So you do the same thing for every single bit.
You do that for the AND, for bitwise AND as well?
Yeah, bitwise AND is the same way. So in this case, you're basically combining those two. So if you want to look at this from the spreadsheet perspective, it would look like this. Okay, so 1 is 0, 0, 0, 1. That is 1 shifted by 0 times. The other one is 0, 1, 0, 1. Oops, 0, which is 1 shifted twice. So when you perform a bitwise OR operation, then you're looking at 1 or 0 here. 1 or 0, which is true or false, is true. Okay, so we have a 1 here. This one is 0 or 0, which is false or false, which is false. This is true again. This is false again. So you have now 0, 1, 0, 1, which is exactly 1 plus 4, which is 5. Is that okay? All right. Okay. So that's a bitwise OR operation. So getting back to my notes here. So is that okay so far? But I don't like this operator because a modulus operator implies division. Division is not easy, okay? Compared to many other operations, it's not easy. So instead of doing this, I could do the following, okay? So this operation is exactly the same thing as M2 equals to M2 ampersand, which is bitwise AND, with the following quantity. 1 shifted 52 times, just the same as last time, but I'll use extra parentheses because I can never remember the actual priority of these operators. Okay, so what do you think is that? Okay, let's focus on one part at a time, and we'll work our way from the inside out. This we know already. It is 1 followed by 52 zeros as a bit pattern. Is that okay? So what happens when you subtract 1 from that? You get all 1s, right?
Yeah, 0,
But how many 1s are we talking about?
51.
Hmm? 52 ones,
yeah,
okay?
there's just 1 extra.
Right, exactly. So now we have 52 1s, and then the rest, the more significant bits, are all zeros. Is that okay? What am I doing with this? I'm doing a bitwise AND of M2 with this thing. So effectively, what am I doing?
You're getting rid of the first one, but then the rest stay the same.
Exactly. I'm getting rid of all the more significant bits. Anything that's more significant than bit 51 gets chopped. But I'm preserving bit 0 to bit 51 because when we're counting from 0, you only have to count up to 51 to have 52 items, right? So it means these two operations are the same. This is doing it from the perspective of arithmetic operations. Is a division, or there's an implied division. This one is much faster because it is done using bitwise operations. Bitwise operations are just like that. They're faster than addition and subtractions. Is that okay? So even though in terms of the result, they do exactly the same thing, but in terms of efficiency, this is a lot faster. Someone may complain and say, yeah, but modern day compilers are pretty darn smart and they can look at the first one and figure out, hey, we can do a bitwise AND instead of the actual division. That might be true. There's an optimization technique in compilers called peephole optimization, and some compilers can do it, can actually optimize this code and make it very efficient. But if you can actually do the simple conversion here to make it far more efficient, why not? Okay. Is that okay so far? Yep.
So, maybe I'm getting this wrong, but was M2 already filled with zeros up to 50?
M2 is...
Was it filled with ones already?
M2 at this point is guaranteed to have exactly 53 bits. So the least significant 53 bits of M2 is filled with zeros and ones. But we are also guaranteed that bit 52 is a 1. Now bit 52 is a 1 is guaranteed because of the algorithm here. Because by the time it is done with these two loops here, bit 52 is guaranteed to be a 1. Is that okay or not? Now, this discussion relies heavily on whether you understand which bit, how the individual bits control or determine the quantity that the number is representing. Okay, 2 to the power 52 is bit 52 in a binary number. Is that part okay? No questions about this? Okay, so I'm gonna make that assumption for now. If you have questions, you can go ahead and ask me. Okay, so at this point we have figured out the fractional part of the mantissa, but the exponent is still wrong. Okay, so let me fire up my document camera, because for this sort of thing it is helpful to just kind of hand draw the whole thing. It would be really cool if they make a document camera that can self-transform. So it's just a little box, you press a button, and it will transform itself into the document camera. I will totally buy one to make one like that. Just for the cool factor of it. And not going through all those really convoluted transformation in the movie, the Transformer, the movie. I mean, when I was watching Transformer, the TV series, the animated, the actual hand-drawn, the poorly hand-drawn, animated series, the transformation sequence were very simple. It's like 5 frames, we're done. And then you go ask, how come this rectangle became a circle? And the size is entirely changed, because they couldn't figure out all that stuff, right? So they just kind of went for, okay, just in general, this becomes, this part of the car becomes that limb. But the proportions all changed. Okay, so let me go get a pen and we'll adjust. Okay, that's good. All right. All right. Okay, so now I have to remember what I was trying to explain. There we go. Okay. So here's your 64-bit of the floating point number. So let's look at this entire range as a 64-bit thing. You can have M2, okay? Your M2 can take up the entire 64-bit, which is great for minimizing errors when we're dividing by 10 or dividing by 2, but we don't need all these bits, okay? Because in the end, what we want M2 to be is this, okay? We want it to become something that's like this. The 1 point is implicit, okay? So the 1 point is not even a part of the box because it is not represented in the box. It is not a part of the number itself. But the rest of the mantissa is. So we want M2 to be shrunk to only this portion, which is going from bit 0 all the way up to bit 51. And that counts for 52 bits. Is that okay? Yeah.
Why is the 1 point implicit? Because you can have scientific notation numbers that don't begin with 1, right?
That's a good question. There's only one number you cannot represent using the implicit 1 point of the mantissa. 0 itself. So as it turns out, the double representation, if you go for the actual equation, that looks at the bit pattern and then look at the value that it's representing, it actually cannot represent the quantity of 0. So they have to quote unquote hack the representation and just say that, okay, if all the bits are zeros, it really means 0 and not a very small quantity that is close to 0. Because that's the closest you can get to a 0 if you go strictly by the representation. So you're absolutely right. This 1 point can cause problems. But they would much rather make that special case than having this one explicitly represented, because now it takes up 1 bit that for the most part is going to be useless. Yep.
I don't know, I might have missed it, but why are we representing 51 instead of 52?
Because we're counting from 0.
Oh, that makes sense.
Yep.
And when you say 1 point, you mean like 1 point isn't like in binary, so it's like the
It's, yeah, these are all binary.
Oh, okay.
Correct.
Okay.
Yep. So this bit is actually this bit here is representing halves. This bit over here is representing quarters and so on. Okay. but they all have to be multiplied to 2 to the power of whatever the exponent specified. So this is just the mantissa itself. Okay, so now the question is, how do we shrink it? Okay, now on the other hand, there's also another scenario where after all the other operations, your M2 turns out to be pretty small. It doesn't use up all the bits at all. So, given these two cases, given the first case, we have to shrink it. Given the second case, we have to make it bigger. But in the end, we want M2 to look like this. This is the objective. We want M2 to look like this, so that it becomes a number that starts with a 1 that is not represented, and then followed by some zeros and ones. 52 of those, to be exact. Is that okay? All right. So switching back to the notes here. So when everything is done, we end up with a value. M is actually between these two values. It is not 1 point something. So how do we make it 1 point something? Okay, so getting back to this picture. So what I'm saying is, when we're done with those two loops, what we end up with here is an M2 that is guaranteed to have a 1 here in bit 52. Okay, the rest we don't know. It's a whole bunch of other bits here. Can be zeros, can be ones, but we are guaranteed to have a 52 here. This is how we can guarantee M2 to be between 2 to the power 52 and 2 to the power 53. Is that okay? So after the two loops, we end up with the bottom represented. We end up with the bottom bit pattern. Where's the implicit point of that particular number? It is all the way here, right? Because it is an unsigned integer, which means it is not, the implicit floating point is here. So what do we need to do? We need to shift the binary point. Is not a decimal point anymore. We have to shift the binary point, how many times?
51 or 52 times, right?
This is bit 0, this is bit 51. So we have to shift it exactly 52 times. Okay, we have to shift it 52 times. So we have to shift it once, twice, third time, fourth time, all the way until it is right here. And that's 52 times. But every time we shift the binary point to the left-hand side, what are we doing to the value represented by that number?
Are you making it smaller?
We're making it smaller, but I don't want the value represented to be smaller. So we have to
E bigger.
We have to increment E. But I don't have to do it step by step, because I know from here to here is exactly 52 times. So that means I can just pretend that we are shifting the period all the way here, and then we just adjust E2 by increasing it by 52.
Yeah.
Is that okay? So that's why in here I just say get rid of the most significant bit, add 52 to E2, and we are done with the mantissa part. Is that okay so far? I can give you an example later. I mean, we can work out some examples. All right? So far, so good? Yes? No? This is what we do in interviews. Sometimes they would ask, in an interview, after an interviewee gets out of the interview, I would be responsible for the technical answers. So the rest of the panel would ask me, okay, so what do you think of that technical answer? So I usually have 3 choices: thumbs up, sideways, or down. And you guys can use the same notation in this class. If you guys see a lot of sideways or down, then I can, okay, let's try to explain it in a different way. Okay. So if this part is done, then we have to calculate the actual E. The E part is actually what is going into this portion. Okay, so this portion here is E. E itself is not a signed number, it is unsigned, but it is biased, which means you take whatever unsigned number is going from bit 52 to bit 62, okay? There are 11 bits. You take the 11-bit unsigned number, you subtract 1023, that becomes the actual exponent of 2 that you want to represent. Is that okay? Yep.
Subtracting 1023 because that's like the 52 that moved over, right?
It's biased by that amount. Now, why is it not 1024? I have no idea. But it's 1023, that's the standard. Okay, so switching back to the notes, because we know this is the actual exponent that we want to represent, but the number that you can put into the bit pattern is E, which is biased by 1023. So once we know this equation, then we can say, oh, the bit pattern, the 11-bit that we actually need to put into the double is going to be E2 plus 1023. That's just your algebra, right? You're taking you're adding 1023 to both sides of the equation, so you end up with E equal to E2 plus 1023. So E2 plus 1023 is what we actually want to represent as an 11-bit number, and that 11-bit number will live within this portion of the 64-bit double representation. So it's going to go from bit 52 to bit 62. Okay, all right. So now we just have the sign bit left. So the sign bit is just bit 63. It's a single bit. If it is a 1, it means the overall quantity is negative. If it is a 0, it means the overall quantity is non-negative. We have to shift this E so that it is going to fit within this portion, and the other one is just M2 itself, which is already in place because of the work that we have done at this point. So bitwise OR and bit shifting can be very useful to combine all of these elements into one single thing that we call double. Is that okay? Okay so far? All right. Okay, so earlier in the class, I was asking you guys to decide, what we want to talk about today. Now that I'm done with this entire module, you guys can think about that and make your decision. Do you want me to give you more examples of double representation, or do you want me to go forward and start to talk about the smallest memory units in the computer?
Examples.
More examples. Okay, so it sounds like it is unanimous, okay, which is good. So I'm going to pass the row sheet. I keep forgetting to pass the row sheet. Yeah, so.
We've done that once?
Yeah, I don't remember. All right, so let's use an example and try to figure out how certain values are represented. And to do that, I think the best way to do it is using a spreadsheet. And the best spreadsheet I can think of to use is Google Spreadsheet, as long as Google is still up. Right? Well, they had a glitch earlier, like yesterday or day before yesterday. They had some major glitch. So.
Shutting down Google Drive. They're shutting down Google Drive.
Sorry?
They're shutting down Google Drive.
They are. Yeah, they were. Yeah. Looks like it's back up again now.
Yeah, not they're actually shutting.
Yeah, it's just like down.
I think they're gonna have Google Lens take over.
Oh, okay, they actually are shutting.
They're actually shutting down.
All my stuff will transfer, right?
If you transfer before they shut it down.
All right. So what we'll do is we'll use a spreadsheet to take a look at how do we translate from base 10 to base 2. How do we change from scientific notation in base 10 to binary representation using a double, and how the individual parts of the double is going to work. All right. Okay. So it may or may not work entirely because there are limitations to the base conversion engine inside Google Sheets. It has a base conversion engine, but it has limitations. All right, so what we'll do is I'm going to do here as base 10 scientific notation, just so that it is clear what each thing is. So I want to comment everything. Okay, and we can make it a little bit bigger. Okay, so it's easy to read. Okay, so let's say we want to deal with negative 2.685 let's make it a E10. There we go. Okay, so it changed it a little bit. I can change the format so that I can get back to what it really should be. So go to format, number, scientific. But I want more precision, so we'll just have more digits here. There we go. That should do it. Yep. Okay. So that works. So if we all agreeing that this is okay, even though the E is an uppercase instead of a lowercase, but it's scientific notation. Okay. Okay. So the first step we need to do is to parse the thing, which is your homework assignment. So in this case, after your parsing subroutine is done, what is going to be your M10? 2685, right? Okay, very good. What about your E10, the exponent of 10? It is 10 to begin with, but we have to adjust it, right?
Like plus 20, 10, 23?
No, it's 10 minus 3. It's minus 3 because every time we shift this period from here to here, we are multiplying the whole thing by 10, so we have to compensate by subtracting 1 from the exponent. So your actual exponent should be 7. Okay, that's the exponent of 10. Okay, it's 10 to the power. So basically the number is now represented as 2,687 times 10 to the power of 7, which is the same thing as 2.685 times 10 to the power of 10. Is that okay? So I'm just changing the multiplication from one side to the other side. The sign is easy. Okay, the sign is just anything that is non-zero, I'll make it a 1. Fine. Okay, there we go. So are we still doing okay so far with this representation? So your homework assignment at this point is to come up with these. That's it. Okay, that's your current homework assignment. So assuming that your current homework assignment is done and you have these components already, now we have to think about, okay, so how do we convert this into the internal double representation? That is the next step. Is that okay? All right? Okay. So you look at this E10, and then you say, which algorithm or which branch should we take in the class notes? So we switch back to the class notes. Where is it? Oh, it's the first one. There we go. It's the same tab. It's the same thing. It's just a different tab. There we go. So we go back to here, and there are two ways to proceed. We can either take on 5.2.1 or 5.2.2. The only difference is one starts off with an exponent of 10 that is more than 0, and the other one starts off with an exponent of 10 that is less than 0. Which one should we use?
More than.
The second one, right? Okay, so we look at the second one, and then we try to follow these instructions by hand. Okay, so we say as long as m is not less than, m by the way is m10 at this point, okay? So as long as m is not less than the largest integer divided by largest integer value divided by 10, do the following. Okay, so the first thing we need to do is to figure out, okay, what is the largest integer value divided by 10? Oops. I keep using the Alt tab here when it's really a different tab on the browser. Okay. So I'm going to do this part here, largest and divided by 10. Okay, there we go. All right, so how do we figure this one out? Well, it depends on what we call to be the largest integer. If you really want to minimize the errors of division by 10 and stuff like that, you want it to be as large as possible. So you're looking at 2 to the power of 64 minus 1, the whole thing, divided by 10. Okay, that should be the quantity that we specify here. So we'll do the calculation. So we are looking at 2 to the power of 64, and then the whole thing divided by 1. But we also have to divide this entire thing by 10. So we take another pair of parentheses. And then say this the whole thing divided by 10. So it turns out to be that number, okay?
Big number.
It's a big number, yep. But this is actually consistent with what I talked about a little bit earlier. that a 64-bit unsigned representation will have about 19 decimal digits. Because this is already divided by 10, it still has 18 digits, so it's about right. Okay, my guesstimation was about right. Okay, so now that we have this value here, we can play with it, right? So when we go back to the, okay, I keep going to the wrong place. So when we look at this instruction here, it says, let's go ahead and keep, as long as m is not less than the largest integer value, which means we're looking at, we need space to do it. So the question, I keep doing this, darn it. Okay, I have to break out the tab into its own window, then all tab would work.
You can do it.
Yep. Okay, so the question now is m, which is m10, is it less than the quantity that we just computed?
Yes.
Clearly it is. Okay, so that means we don't have to get into the loop at all. We can just go ahead and go to the second step. So we go to the second step. I keep doing it. Okay, I'm gonna do it. Move to new window. Okay, now we can all use Alt tab. Between this and, oh, okay, I need to switch to the right tab first here, which is this one. There we go. Okay. We're done with the loop. Okay, we're done with the loop because m is already less than the largest integer value divided by 10. This condition is not true anymore, so we move on. And to move on is easy. We just multiply m by 10, and then we store, we track e10 to be 1 less than what it is currently. Okay, so that means I need some columns to track all of these things. So let's go ahead and track m. We track e10. M is this number to begin with initially, and e10 is this number to begin with. After the first iteration, what do we have? We are multiplying m by 10, decrementing e10 by 1. So this becomes this thing times 10, and this becomes this value minus 1. Is that okay? This is why I like to do it in a spreadsheet, because I don't have to do my own calculation or to do a whole lot of typing. Is that okay? All right. So, but when do we stop? We stop when e10 is 0. Okay? How do we know that? Because right here, all these steps need to be in a loop that repeat as long as e10 is greater than 0. Okay? So e10 is not 0 at this point. Let's do it one more time. This is where a spreadsheet comes in really handy. Not yet, right? Not yet. Not yet. Well, I mean, you can tell how many more rows we actually need. I'm just being dramatic here. Well, being as dramatic as an INTP can possibly be. Okay, so we're done now, right? Because because e10 is a 0. M is really kind of big, but it's okay. We can deal with that later. Are we okay so far? So we are now done with section 5.2, which is getting rid of e10 or turning e10 into a 0.
Was it 6 zeros? 6 zeros more or 7?
7 zeros. Yep, 7 zeros. All right, are we okay so far? So I'm gonna, document this part here, okay, and say format merge cells, and call this one, section 5.2, because that's what section 5.2 is doing. And later in the class, I can just share a link to this document with you, so you guys don't have to write anything as long as we are still streaming. So it's still streaming, and it's recording the voice just fine. So you don't have to write down anything like that. Okay, which helps, right? Because the spreadsheet can update faster than you can write by a good margin. Okay, so this is all in section. Okay, I'll make it more clear. Why is it 5.2? It's section 5.2 of the notes. Okay, just to be more clear. Okay, after section 5.2, we move on to section 5.3, which is to normalize the mantissa. So the normalization of the mantissa means I want the mantissa to be greater than or equal to 2 to the power 52, but less than 2 to the power of 53. Okay, so those two values become particularly useful to me. So in the spreadsheet, I'm going to use another 2 rows of constants just so that I know what constants I'm dealing with here. So on this one, I would just say this is 2 to the power of 52, which is the minimum of that range. And then over here, I have 2 to the power of 53, which is the maximum of that range. I want m to be between these two. Is it between these two right now? No. Not even close, because we got 2.685 times 10 to the power of 10 to begin with, right? So we're a little bit off. So we'll make the adjustments one step at a time. Okay. So we'll say, okay. So we'll first evaluate whether we need to double it or not, and then we'll go ahead and double it on the other side. Okay. So over here, I'm just going to evaluate the condition. So I would say, okay, that's pretty easy. Is this less than this? True. Okay, so that means I need to double. Okay, is that okay? So we'll say equal this times 2. But I have to do one more thing now. I have to adjust the E. So I better start a new column to document E2. E2 starts off with a value of 0, right? But now, because of the doubling here, I have to make it -1. Is that okay so far? Okay. And on the next row, what are we going to do? Pretty much the same thing, except I need to do one little thing before I replicate this. Because if I just use the same mechanism as last time, it's going to refer to this row for the comparison, which is not what I want to do. So that means I have to change this one, put a $sign to the row reference. So put a $sign here. The other one is fine because I do want to. Yep, the other one is fine. So we want to.
I want to just make it compare to the column on the left, otherwise it's going to be staggering and weird.
It is comparing correctly now. Yeah, when you double click on the cell, it would color code the reference cells as long as it's visible. So now we can see which 2 cells it's comparing, and that's correct. Okay, it's comparing the correct cells. But because the answer is true, we also want to keep doubling this, right? And then we have to decrement this one more time. So now instead of using my own calculation, I'm just going to say this is this minus 1. Is that okay? So what I'm going to do now is to keep doing this until it is false. In other words, I'm just trying to determine how many times I have to go through this loop. Oh, because it's not comparing correctly. So I have each time I have to adjust that. No, it's comparing just fine. Yeah, because of the dollar, it is not. Oh, okay, there we go. We have the false here, so we have to stop here. Okay.
Which one is it? Oh, okay, never mind.
Yeah, this false is basically saying that is false already, and that should get us out of the loop. So we are done here. But we also have to extend E2 all the way down to that particular row. There we go. So are you guys buying this is all working correctly at this point? I'm not buying it. I want to double check. How do I double check?
Double click the false.
No. Well, that would double check and make sure that the quantity that we have earlier here is this is no longer less than that. Okay, which is fine, and we can visually see that this value is between these two. So that's cool. But I'm more worried about, are we still representing the same value as before? That is what I'm worrying about. Okay? Yeah, we can just go through the calculation, right? So the calculation, I'm going to put it over here because it's really just a kind of ad hoc calculation. I just want to double check everything. So the value represented right now is the base 2 mantissa, which is this one here, times 2 to the power of this particular value. Okay, 2 to the power of that. And that turns out to be the same value that we started off with. Okay, which is great. Okay, so that means I didn't do anything wrong in the process. You know, everything is still representing the same value. It is also important. This step is also important because it is also helping me to illustrate to you that with all of these manipulations, we are not changing the value being represented. We're just changing how it is expressed. Okay, all right. Okay, so now that we're done with this part, which is corresponding to in the notes, you know, section 5.3, almost done. Okay, we're almost done because we also have to chop the bits, right? You know, we have to chop the bits here, and we can do that by a mod operation because the spreadsheet doesn't really have a bitwise AND operation. So you know, I don't have a choice but to use a mod. Okay, so over here I'm going to do the mod operation, which is modulus, and we have to specify the dividend. I'm not sure whether it can handle a range of number like this. To the power 52, and yep, it can do it. Okay, very good. So that is this number now, and then the E also has to be adjusted. So now we have to look at this E. Okay, look back at the notes here. E has to be incremented by 52 because of all those implicit shifting of the binary point. So now we look at this number and say, let's add 52 to it because we are implicitly shifting by 52 positions.
Now we check to see if we get the same value as the beginning.
Now we cannot really check anymore because, you know, if you want to check, we can, okay? But the way to do it is a little bit different now. Because the way you do it now, if you want to check, because this bit pattern is no longer is now representing all the digits to the right hand side of the binary point. Okay, so you cannot just take this number and multiply that anymore. So when we check, now we have to say 1 plus, okay, this value divided by 2 to the power of 52, okay, because that's the implicit denominator. Is that okay? Hmm?
Why is it implicit denominator
You need
again?
another parenthesis.
Yes, I'm not done yet. Yeah, so and then the whole thing has to be multiplied by another power of 2 times power 2 to the power of whatever this number is specifying, because that's our E2 that is already normalized. Okay, and we got the same value back. So it still works. Okay, so I'm kind of glad that you asked the question, you know, can we double check the value being represented? But it's not the same as the previous one because the bit pattern of column B is really only the portion of the mantissa to the right hand side of the binary point. So the first digit is now representing a half. The second digit is now representing a quarter, and the very last digit is representing how many to the power of negative 52 that we have. Okay? So that's why I have to divide the entire thing by 2 to the power of 52 and add 1 to it. That 1 is the one point that is implicit. So that becomes the actual mantissa in base 2, the normalized mantissa in base 2. And then the power, which is column F, 2 to the power of 34, is the actual magnitude of the number once we have the normalized mantissa in base 2. Whew. Is that okay? But we did double check everything. Everything is still in order. Okay, so that's great. What else do we have to do? Well, we got everything done here. So this is section 5.3. So I'm going to go back here and just kind of merge all of these cells just so that it is easy to see that that section corresponds to section 5.3 in the notes. So we go to Format, Merge Cells, and say this is all in section 5.3 in the notes. All right, so now that we have all of these things, we can move on to section 5.4. 5.4 is easy. We just want to compute E. Okay, so let's go ahead and do that. So we just say that, okay, I'm just trying to find out where to put it. Maybe here, okay? So E is really just this value plus the bias, which is 1023. Is that okay? In other words, the 11 bits in the number from bit 52 to bit 62 as an unsigned number needs to represent the quantity of 1057. Okay? Not okay? Sort of okay? Okay. Well, let me label it first, okay, just so that, you know, if we need to, we know that this is corresponding to section 5.4. So section 5.5 is the last thing, which is, you know, putting the whole thing together, right? Okay. So when we go back to section 5.5, we want bit 63 to be the sign bit, we want bit 62 to 52 to be the exponent, and we want bit 51 to bit 0 to be M2, and the current M2 is okay, it is correct. Okay, so the question is, so what kind of bit patterns are we talking about, and how do we merge all of these things so they become one gigantic, you know, huge binary number? Okay, so we'll work on one section at a time. Okay, M2 as a bit pattern. This is the great thing about using a spreadsheet, but I'm not sure whether it works or not. It has dec to bin, decimal to binary. So we can now just say, go ahead and convert this number, and but we want a fixed number of bits. Okay, we want all the leading zeros. If there are leading zeros, we want the leading zeros because we want to look at this as a string later on. So we need 52, exactly 52. I'm not sure whether this works or not. No, it doesn't like it. Yep, it says right here, the valid values are, oh, that is such a small range. Ay, caramba. What are we going to do with this? Well, I can chop it up and do it like section by section, which is going to take a long time. Okay, this is bad.
Well, that's like a standard format for like the writings. Maybe you could find another thing that would take it.
Sorry?
Like, that's like a standard form, so maybe there's other generators and translators that can do it online.
Oh, we can probably do it to hexadecimal and we get this.
Yeah, but we might be able to do it. Okay, so let's see. Dec to hex, oops, equal to dec to hex. Okay, so we want to start with this number. It might have, I think it's going to choke too. Okay, 52 bits corresponds to how many hexadecimal digits? Divide 52 by 4. That's basically what you need to do. 13. Okay, so we need to be exactly 13 bits, 13 digits wide, and it doesn't like it either. Okay, let's see what it's complaining about. It has a much bigger range, but we are still exceeding that range. This is the problem of using the spreadsheet, because it just doesn't have the representation. You know, it doesn't have the functions, you know, to do it. GDB can do this pretty easily. So that's the other way to do it. We can use GDB to do it.
Can we assume that most of the last numbers are going to be zeros anyway, and it's really just a range?
Well, we are not sure about that. Okay. Because these are all done by multiplication by 2, which will not affect the number of zeros. So you're correct. We might be able to use that as a fact. Okay. So let me see if I can look at this number, you know, slightly differently. So we'll say this is the same as this, but we don't want scientific notation here. We want the actual, you know, entire representation. So we go to format, number, and we just say this is a regular number. Okay. Yep. So now we can get the exact, you know, format, which is good. Okay. So now unfortunately, I can't do this part in inside the spreadsheet, so I'm going to have to cheat and go to GDB or any type of, you know, C-based, you know, engine to do it. So I'm going to copy this, switch to a command line prompt and just do a GDB, and we want to say print. Let me make sure that I can paste that number. Yep, I can do that. Cool. Okay. So what we want to do is to look at this as a base 2 number, and it's /b to specify print everything in binary. But I'm not sure whether this will give me all the leading zeros. Okay, print. There we go. /t is binary in this case. So it gives us all these zeros and ones. Okay, that's one. And then the other one is this one here, 1020, 1057. Okay, so I'm going to combine all the steps into one, and then we'll chop it up again, when we need to. So this needs to be shifted by 0 because everything is in place already. This is our fractional part of the mantissa. The other part is going to be our exponent, and this is our exponent. So we just put 1057 here. But this one does need to be shifted because this is our exponent, which is starting with bit 52, ending with bit 62. So we have to shift this 52 times. Okay, are we okay with why we are shifting this part by 52 times? Because the least significant bit of E is bit 52. But without shifting, the least significant bit is at bit 0. That's why we need to shift it 52 times. And then the last one is the sign. The sign is a 1 shifted 63 times because that's just bit 63.
Do you need to put it in binary or?
Well, this might work. Okay, it looks like this is going to work. But looking at it this way is not going to be very helpful. So this is the actual binary representation of the value that we need to represent. Okay, does it look right? That's the question. You go like, maybe. Well, let's check.
That's good.
Let's eyeball it. Okay, let's eyeball this and see whether it makes sense or not. This is the most significant bit, which is a 1, which means the overall value is negative. Good, right? And then we look at this value here. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So is this representing the value that we wanted to represent, which is 1,000 something? That doesn't look right to me. Yep.
And the second one, I just copied the same one from the top. They're identical.
Yeah.
Say again?
Yeah. The top one,
Well,
and they're identical.
Just the integer.
It just printed the first one again.
What?
It just printed the 253. It just printed that again because if you look at line S2, it's the same thing.
SS4.
Oh, okay. $3 and $4 are the same.
S2 would be the integer.
But $2 and $4 are the same.
Yeah.
Yeah.
So it didn't do
It didn't
all
print
the.
correctly.
You didn't do it.
It did not do the OR correctly.
Maybe you have to
Okay.
maybe wrap the whole thing in parentheses.
And I think it has to do with it has to do with the size of the implicit size of an integer. Okay, so I'm guessing this is not going to be okay. Okay, so why is that?
Oh, is it like going
Okay,
to
I'll give you the answer.
overflow?
Because because in GDB the implicit size of an integer or the implicit width of an integer is 32-bit only.
Oh.
So when your entire integer is only 32-bit wide, and you're shifting by 52 times, what do you get? You get 0, right? Because you have shifted everything useful out of the number a few, like almost 1.5 times. Okay. All right. So
Can you turn it into
Yeah, can you
64-bit?
tell it to do something?
yeah, we can fix this. So you just say unsigned long, and we just have to cast all the numbers with unsigned long. And of course the last one is especially important.
Yeah.
Okay, there we go. No!
Unsigned long.
Okay, so now we have to look at the size of. What is the size of an unsigned long? Oh, okay, that doesn't work. Long, yep. Sounds like a musician to me. it would be totally inappropriate to walk up to Long Long and ask, "Are you signed or unsigned?" He's gonna whack you with his musical instrument. There we go. That looks better. Yeah? It looks a lot better, okay? Because when you look at this portion here, I'm just doing a sanity check. 5, 6, 7, 8, 9, 10, 11. I lost count. I think that's 11. There we go. Okay, so when you look at these as 11 bits, the most significant bit here, the highlighted portion, is 1024. It specifies the amount of 1024. So we have 1024 plus 1 plus, let's see, 1, 2, 3, 4, 5. So it's 2 to the power 5, which is 32. So we have 1024 plus 32 plus 1, which is about the same thing. That was
It's exactly the same.
Yeah. So we're cool. So this is a sanity check, just to make sure. Okay.
And then we're not going to do that second part.
Sorry?
And then we're not going to do that third part.
Well, so the next thing we're going to do, so the next thing we want to do is to look at it as a hexadecimal number, which is 0x02 C219 da 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 da. So I can't do the trick with converting this into a double, because everything here is not stored in memory. So I cannot just say, hey, take the address of this and pretend that it is something else and store something into it, like the trick that I did before. With this one, I'm just trying to see if I can. There's no way to cast it, because if I cast it to a double, it would actually do the value cast, not the internal representation cast. So there's no easy way to cast it. So I'm just thinking, okay, so what we'll do is we'll store this. Okay, copy it first. And we actually need a program to do it. We need a program to give it a storage. So we'll say test.c double D, return 0. That's more than enough. As long as the C compiler is convinced this is more than enough, it's going to complain. Okay, it's going to complain about the variable declared but never used. It's okay. Okay, we know this is coming. Okay. All right. So list the program, put a breakpoint on line 5, run the program, because all I really need is just that space. Right. Yep. So now we can say set var d reference unsigned long address of %d equals 2, and then paste. There we go. Candidate address of d, which is in the value, which is in the L value. But these are L value. Oh, I think it optimized it out. Smart ass compiler. Okay, let me see if I can convince it not to do any optimization. So dash uppercase O and then the 0 means do not optimize. Okay, if I say declare a local variable, give me a local variable. Hopefully. Okay, so it still knows it's not used. Okay, which is okay. The question is, do I have it? I hate this. Okay, such a smart ass compiler.
Can you just assign it a value?
Yeah, that would fix it, but I was trying to avoid that. It will still complain and say that this variable was assigned a value but never used. See, but at least it would exist. That's my hope. 6. There we go. Print D. Yep. So at least it exists. So now we can go back to. Okay. I cannot up arrow back to that. Okay. That's okay. Set var D reference unsigned long address of D equals to paste. That works. Print D, and we get we got most of it back. So is that okay? I mean, that really concludes the whole demonstration, even though most of it could be done in a spreadsheet, the last little bit cannot.
Weird that it's an 8.5 at the end. Why is that an 8.5 at the end?
Well, remember, this is converting from the binary representation back to base 10, so that process introduces errors as well. So we have errors going in, and then we have error coming out. So, but when you look at the precision, it's not too bad. It's okay, you know.
11 or 12 decimal places.
Yep. When you look at the percentage of the error, it's not too bad. Yep. So, are there any questions about the process that I just demonstrated? Because it's just really, you know, going through the logic, doing everything by hand for the most part, but I use a spreadsheet to help me with the heavy lifting. But the process is still by hand. I'm still evaluating, okay, should I go for another iteration? Yes, okay, go for another iteration. So for the most part, it's by hand. But you can also see how most of the processes are very mechanical, which means you can do it with a program, which also means you know what the next homework assignment is going to be about. Yeah. Is that okay? All right. So we got 5 minutes left. Are there any questions about the process of, you know, first parsing the base 10 scientific notation into the format that we want, and then the second one is look at the numbers that will be the output of your current program, and then use those values to do the actual conversion to the double internal representation. No questions? Now I know this stuff, you know, is not, you know, a walk in the park. Okay, you know, there's a lot of details involved, and a lot of notations. I know there's a lot of notations in my notes, but that means you just need to spend more time to read the notes and not just glancing, but actually understanding the content. And that really goes all the way back to my syllabus at the beginning of the semester. Is, you know, the most important part is not to just to read the notes or to re-listen to the lecture, but really to understand what the symbols are, what I'm really trying to explain, and so on. That is the most important part. All right. No questions? Really? Okay. Well, with 5 minutes, we can at least get a little head start on the topic that we'll be going into next week. Just to give you a little head start, you know, just to show you what we'll be talking about. So we'll be starting off with what we call an SR latch. Okay, I have my notes being typed up already, but you know, I will just give you, you know, the ideas or the terms, so that, you know, by the time, you know, I get your notes, you know, ready, you would know that, oh, okay, this is what we're going to be talking about. So we will start with the concept of an SR latch. An SR latch, you know, can be implemented using NAND gates. Okay, and it's just like that. Okay, I'm just click on one. You know, they are all about the same. Okay, this is a SR latch. Do you notice this to be different in a very fundamental way from all the other gates that we have dealt with? Even the look, you know, the carry look ahead adder. There's a feedback. Yeah, look at this thing here. The output of the top NAND gate becomes one of the inputs of the second NAND gate. The output of the second or the bottom NAND gate becomes one of the input of the first NAND gate.
How does that work?
So this is really kind of weird, right? Because we have some kind of a feedback here. But it doesn't go back to the same gate, it goes to the other gate, okay? And this is the essence of a memory device, is it has the ability to have a feedback to itself, to quote-unquote reinforce / maintain its own state as a result. Okay, so when you look at this design, okay, you know, just looking at this, you know, and just analyzing it, you know, casually. What happens when S is a 0? These are NAND gates, by the way. What is guaranteed to happen?
What do the results start
One
as?
goes into the.
It doesn't matter, because when S is a 0, okay, when S is a 0, this is a NAND gate, right?
Sure.
With a NAND gate, if any input is a 0, the output is going to be 1. Very good. So when S is 0, Q is guaranteed to be a 1. Would that impact, you know, not Q? Maybe, maybe not, depending on what R is, okay? What happens when R is a 0? Same thing, right? When R is a 0, the Q bar is going to be a 1, okay? So when S is a 0, R is a 0, then Q and Q bar are both going to be 1s, guaranteed, okay? So that one doesn't depend on the feedback because we only need one of the inputs to a NAND gate to be a 0 for the output to be guaranteed a 1. Is that okay? So that part of the analysis is easy. So let's say that is the first step. So the first step is S and R are both 0s. And then you turn one of them into a 1. Okay? And then you turn the other one into a 1. So I would just suggest that little mental exercise. Okay? So you basically look at the whole sequence of operation of SR both being 0s, and then you branch out. Okay? In one branch, you turn S into a 1 first, and then you turn R into a 1. In the other branch, you turn R into a 1 first, and then you turn S also into a 1. And then you see what is the result. And they're different. Because even though in the end, both S and R are going to be 1s, the state of this entire device is different. In one case, Q is going to be a 1, Q bar is going to be a 0. In the other one, Q is going to be a 0, and Q bar is going to be a 1. Even though the inputs are exactly the same, 1, 1. That is what we call a latch. And it is the smallest memory device because when the input is 1, 1, it is only maintaining its current state. And that's something that our current gate logic doesn't do. Because our current gate logic, with the adder and the subtractor and stuff like that, the moment you change the input, the output changes. But this one allows you to maintain the state of the output even though the input state is changing. Which also means there's one state of the input called maintain, which basically means do not change the output, keep it the same way as it was. And that would be the 1, 1. When S is 1, R is 1, it is just maintaining its current state. Doesn't sound like it's going to do a whole lot, right? Okay, how do we specify that we want to store a 0? How do we specify we want to store a 1? It doesn't do that, okay? This is just an SR latch. S stands for set, R stands for reset. So it's really just a little mechanism that you can set and reset using the 2 input pins. Or you can specify, I don't want to do a single thing, just maintain the current state, which means both S and R are 1s in that case. Okay? And the next one, we're slightly running out of time, but the next one is called the D flip-flop. And I will have explanations of all of these things next week. But the D flip-flop, does it remind you of something that we just saw?
Yeah, we see the same move at the end there.
It has an SR latch as the second part. So when you look at the second half here, it's an SR latch.
Yeah.
But the way it works is a little bit more intuitive. D specifies, do you want to store a 0 or 1? D controls what you want to store. The clock, on the other hand, is going to enable the storing. So when clock is low, okay, then you can do whatever you want with D. The latch doesn't change its state at all. On the other hand, when clock is high, then whatever you specify in D will change the state of the latch. So now it's becoming more useful because now we can actually say, oh, store a 1. No, wait, hold on, store a 0. Is that making any sense, sort of? No? Okay, fine, that's okay. We'll take a look at this next Tuesday, okay? So next Tuesday will be the beginning of the discussion of memory units inside the computer. And we'll start with the smallest unit, which is called an SR latch. And then we'll move on to D flip-flops, and then we'll move on to edge-sensitive D flip-flops. Then we'll move on to registers, and then we'll start to talk about the stuff inside the processor. So we're building a processor from the ground up in this class. Okay, it's not top-down design like your other classes. This is from the ground up. All right, so we're transitioning to the lab so that you guys can work on your parsing homework assignment. And if you have any questions, I can answer those questions, most possibly with Another question.